Hi there. For this video, we will be solving rational inequalities. Now that we are done with polynomials, similar inequations, the next thing that we tackle are rational. But this time, we will have rational inequalities. So just to recall, rational expressions or polynomials or not rational polynomials is wrong, but we express rational as p of x over q of x, where q of x is not equal to 0. So it's like a polynomial over a polynomial. So those are our rational expressions. Like for instance, we can have x minus 2 over x plus 1. Since x minus 2 and x plus 1 are polynomials, so we'll be tackling these types of inequalities. Now, as a initial answer for our question, the key in solving rational inequalities is similar to how we did it in quadratic and in higher order polynomial inequalities. We simply inspect the critical points. So if you don't know the critical points, you may review the previous videos or just skip to around somewhere in the middle of this video, as I will have a recall or review part on what critical points are. Additionally, we also need to take note of the domain in rational inequalities, since in our example a while ago, we have x minus 2 and x plus 1. We know that x plus 1 cannot be equal to 0. So this means that x cannot be equal to negative 1. So that is something that we need to take note when we arrive with our solution set, that the domain need to be remembered in our final answer. So now, before we dive into our examples, let us first recall what critical points are. So again, if we have, say, x plus 1 and we equate this to 0, the outcome will be x equals negative 1. So negative 1 will be our critical point, and let's plot it out here. So essentially, critical points are like the point of change of signs. Because if you observe, if you try to plug in the values out here from the left, say let's try to plug in negative 2, the outcome for this expression will become negative 2 plus 1, which is negative. And in fact, that is true for all the values out here. So we say that this region out here is the negative part. On the other hand, if you try to plug in values from this region out here, say 0, oops, I accidentally erased the expression, so I think that is x plus 1. So if you plug in 0 out here, then we'll have 0 plus 1, which is 1, a positive value. and that is true for every values out here. Therefore, we say that this region is positive. So the critical point is, again, this is the region wherein our given expression is 0. So it's like the point of shift of signs. So that is essentially how critical points work. Let's go on to our first example. Let's have x minus 3 over 2x plus 1 is greater than 0. So, first, our goal is to, similar to the polynomial inequalities, our goal is to leave one side 0 and isolate or move every terms to the one side of the inequality, which is already good in this example since every term or expression, algebraic expression, is already on the left side. And as you can see, we have a rational expression out here on the left. So, how do we solve this one? Well, we first get the critical points of x minus 3 and 2x plus 1. So for the critical points, we just equate them to 0. So x minus 3 equals 0 will give us, just move negative 3 to the right side, we obtain x equals 3. For 2x plus 1, its critical point is, start by moving 1 to the right side to obtain 2x equals negative 1, then divide to both sides, and we obtain x equals negative 1 over 2. There. Now that we have our critical point, so let's box that one. Next step is to plug it in or on our number line. There. So I hope the line is quite straight. Then let's put in the negative 1/2 here and the 3 around here. And the critical points will divide our region into, in this case, 3 areas. So what we do is we check the sign of our given expression in these areas. So let's write that one, x minus 3 over 2x plus 1. So let's have a test value on this area. What is a number less than negative 1/2? But note that negative 1/2 is equal to negative 0.5. So I think it's now easier to see that a number less than negative 0.5 is negative 1. So let's try to inspect at negative 1. At negative 1, in the numerator, we'll have negative 1 minus 3. So the outcome for the numerator is negative. For the denominator, we'll have 2 times negative 1 plus 1. So that will be negative 2 plus 1, which is also negative. So we'll have a negative on the denominator. And negative over negative will give us a positive value. And if it is a positive value, then we know that the outcome is greater than 0. Therefore, we say that in this region, the inequality is true. Next one. Oops. I also erased the given There. Now let's try out at this region in the middle. Since we have a negative and a positive value out here, then we know that 0 lies somewhere in the middle. So let us use that as our test value for the middle region. So at x equals 0, this one, 0 minus 3 will give us negative 3, so that will be a negative value. Then 2 times 0 plus 1, simply 0 plus 1, which will give us a positive value. So negative over positive will give us a negative value. And when it is a negative value, we know that it is not greater than 0. Therefore, the region out here is false, as it was not able to satisfy our inequality. So last one. For this region out here, what is a test value that we can use? So we need a value that is greater than 3. We can use 4. So at x equals 4, then x minus 3 will become 4 minus 3, which is 1, and that will give us a positive value. Then for 2x plus 1, we'll have 2 times 4 plus 1, which is 8 plus 1, which will give us a positive value still. So positive over positive will give us a positive value. So it is greater than 0. So since it is satisfying our given inequality, we say that this region out here is true. Therefore, in conclusion, we know that we'll have x, this region out here, x is less than negative 1/2, or x is greater than 3. In interval notation, that is negative infinity to negative 1/2 union 3 to positive infinity. That is our answer. So just take note here that we had a strict inequality in the given. That is why on our answer we still have strict inequalities. Furthermore, note that for this problem, the domain of the rational expression out here, so we know that 2x plus 1 cannot be equal to 0, or x cannot be equal to negative 1/2. But fortunately, negative 1/2 is not included in our inequality, since our inequality is strict. So we didn't really need the idea of domain in this example. But let us see if we will be needing that in the next one. So let's have this second example. Let's have 2y squared minus 7 over y plus 1 is less than or equal to negative 1. Unfortunately, in this example, we still have one side of the equation that is not equal to 0. So what we'll do is we'll move this to the left. And that will give us 2y squared minus 7 over y plus 1 plus 1 is less than or equal to 0. Then note that we can write y, or rather 1, as y plus 1 over y plus 1. So we now have similar denominators out here, so we can combine the numerator. So we'll have 2y squared minus 7 plus y plus 1 over y plus 1 is less than or equal to 0. simplifying this numerator, we'll obtain, let's move this one, we'll obtain 2y squared plus y minus 6 over y plus 1 less than or equal to 0. And observe here that on the right side, we are already done, since 0 is what we want essentially on the right side. But for the left side, it's still not easy to find the critical points since our numerator is still of degree 2. So we still need to factor that one out. Now you can verify that the correct factoring for the numerator will be 2y minus 3 times y plus 2. And of course, this is all over y plus 1, which is less than or equal to 0. So if you don't know how to do that, this part out here, you may check out my video on factoring quadratic trinomials, especially the last part, since I talked there on the last part of the video about a trick on how to factor quadratic trinomials that has a coefficient on the first term or the second degree term. So this one out here becomes our new version of the given inequality. And now, let's have the critical points. So for the critical points, we simply equate this, and this to 0. So we'll have 2y minus 3 equals 0. That will give us, move negative 3 to the right. We obtain 2y equals 3. Then divide to both sides. And we obtain y equals 3 over 2. So that is our first critical point. Next, this one. So we have y plus 2 equals 0, and that will give us y equals negative 2. For the last one, for y plus 1, we'll have y plus 1 equals 0, or simply y equals negative 1. And now we have our critical points. So we can now go on to our number line. So let's plot in our points. So let's have negative 1 out here, then negative 2 out here, and say 3 over 2 out here. So just take note that you also need to be careful in plotting the points, since if you aren't careful, then the answer might be incorrect. So let's try to have some, let's first split the region out here. So we'll have this region, this split, and this split. So we have region 1, region 2, region 3, and region 4. So let's first have a test value for this region out here. So let's copy this one. That I copied incorrectly. It should be this one. Apologies for that. And there. So let's take a value around here. So we can take a value less than -2 is -3. So let's have here -3. So at -3, this region out here will be 2 times -3 is -6 minus 3. So that out here is negative. Then y plus 2. -3 plus 2 is negative. Then -3 plus 1 is negative. So we'll have here negative times negative over negative. So negative times negative in the numerator is positive over negative, and that will give us a negative value, which is this one, less than or equal to 0. Since it satisfies the inequality, then we say that this region is true. Now for this one, out here, what is a number in between -2 and -1? Now this might seem quite tough since we'll have a fraction, but we have no choice since we need to. So we can take -3 over 2, since -3 over 2 is equal to -1.5, so it is really in the middle of these two. So at -3 over 2, this one out here will have 2. Let's write it out here. 2 times -3 over 2 minus 3. This one cancels, and we'll be left with -3 minus 3, which is -6. So we know that the value out here is negative. For y plus 2, you can use the decimal version, so -1.5. -1.5 plus 2 is clearly positive. And for this one, -1.5 plus 1 will give us negative, since 1.5 is greater than 1. So we have negative times positive over negative. We'll have in the numerator a negative value over negative, which is positive. And it does not satisfy our inequality. Therefore, we say that this region out here is false. Let's have our third region, this one out here. Since we have a negative value out here and a positive value, then we know that 0 lies somewhere in this region. So we'll use that as our test value. So at 0, 2y minus 3 becomes 2 times 0 minus 3, or simply a negative value. 0 plus 2 on the other hand becomes 2, which is a positive value, and 0 plus 1 is also a positive value. So we've got negative times positive over positive, and that will give us a negative on the numerator and positive on the denominator. So negative over positive is negative, which is less than or equal to 0. So it satisfies our inequality. So we say that the region, this third region, is true. Let's go. Last one. Now, it's really a lengthy process in doing this, but as you get the hang of it, it becomes easy and faster to do. But yeah, let's go. Last region. So, at this region out here, what is a number greater than 3 over 2? Note that 3 over 2 is equal to 1.5. So, we can take 2, since it is greater than 1.5. So, at 2, this one out here becomes 2 times 2 is 4. 4 minus 3 is positive. Y plus 2 becomes 2 plus 2 is 4, so it's also positive. And the last one, 2 plus 1 is also positive. So positive times positive over positive will just result to a positive value, which is not less than or equal to 0. So it does not satisfy our inequality, and therefore this region out here is false. So now that we are done with testing out the values, with this one, we can now have our final answer. So our valid regions is the first region and the third region. So we say that y is less than or equal to -2, or y is from -1 to 3 over 2. But is this correct? Well, for the y is less than or equal to -2, that is correct. But take note that if we inspect the domain out here, y plus 1, we know that y plus 1 cannot be equal to 0. Or that means just y cannot be equal to -1. Since if we have -1, then the denominator becomes 0 and our rational expression becomes invalid. Therefore, we remove the equality in -1, since y cannot be equal to -1. Also, just take note that the reason that we have a non-strict inequality is because we are given a non-strict inequality as well. But again, taking note of the domain, we make this one out here a strict inequality. And so that one is the answer. In terms of interval notation, we'll have -infinity to -2 with a square bracket, union, a parenthesis of -1 to 3 over 2 with a square bracket. And this one out here is the final answer for this problem. And yeah, we are done. Quite a lengthy process, but to end this one, here is an exercise that you can work on, and observe here that we have a chained inequality, which we didn't tackle in this video. But I'll leave that to you to explore how to deal with chained inequality. But as a hint, the technique for this one is to split the inequality into this one and this one next. So that is how you split the inequality, and after you split it, you get the intersection of the two inequalities that you obtain. So basically, you'll have two rational inequalities out here. That is why we only have one exercise, since it's already like two rational inequalities. So that's it. And yeah, feel free to comment down below your answers, solutions, and other comments you want in the comment section down below. And I hope you enjoyed this one and learned a lot from it. So that's it, and that is all for this video.